Good morning. Hi, Chris. Good to see you again.
Morning. Yeah,
Been a couple of weeks.
yeah, 3 weeks. Yeah,
Wow.
yeah,
We're,
including spring break.
we're able to keep up.
Yes.
I unfortunately discovered at the end of spring break that I had forgotten to post the video from the Thursday right before spring break. And so it was almost over a week delay before I got that video posted, but it's up now. How are you doing?
Good.
So you were on the road for a while and then came back?
Yeah, did a long road trip. We went to visit family in Missouri and Texas.
Wow. Nice.
So we took our boys on a long trip. We did 11 states, almost 6,000 miles.
Wow.
Yeah.
Gosh, I just went to the coast with my family. Spent 5 days on the Pacific coast.
That would be fun.
It rained about 3 of the days, but otherwise it was nice. Go see Point Arena Lighthouse, and you couldn't really go to the beach because I guess that section of the California coast, that small section, the beaches are actually really dangerous. There's actually signs up there. And we went to one beach that said, "Warning, this is one of the most deadly beaches in California." And the reason for that is the sand drops off pretty steeply instead of a gradual out into the ocean. It drops off pretty steeply, and then there's this trough that the waves form. And so what happens is the waves come in and they churn around in that trough. And so if somebody gets trapped in a wave, they will go into that trough and just spin around. There's signs showing pictures of what this looks like, and it says, like, warning, do not enter the water, do not play tag with the waves, do not, and it's like, and so we're looking around all these people who are staying far away from the ocean, like, this is the saddest beach in the world, right? Because no one can touch the water. But so there was one beach that had those signs posted, and I saw other beaches that kind of had a similar setup, and so I was like, I'm not going to go anywhere near that water. Plus, it's probably cold, so forget that. But I did get a chance to go out and do some ocean fishing, and so although it was raining that day, so ocean fishing in the rain is not that much fun, but nevertheless, we did catch some fish. Enjoy that. Well, this week we are finishing up our discussion of how to crack passwords as fast as possible. And we can go over really quickly what we did the last time we met and then see how we can improve things. So let me bring that up on the screen here, and we'll just quickly zip through the program that we wrote, and then we'll look at some improvements that we can make. Okay, so here's the program that we had. Now, this is all, at this point, one giant main, which I don't really like, and maybe the first thing we should do is kind of break it up a little bit into smaller modules, smaller functions, but let's just take a look at what we've written here. So, if you remember, the purpose of this was to load the entries, load all these passwords out of a file, and then pre-hash each one of those passwords and put them into a parallel array of hashes. So we've got one array of a whole bunch of strings consisting of all these passwords, and then we got another array consisting of the hashes, and there are corresponding entries. So entry number 0 in the entries array corresponds with entry number 0 in the hashes array. And then the goal was, once we had pre-hashed all the passwords, we could then prompt the user to type in a hash to search for. It would then search through this hashes array, and when it found it, it would just look at the corresponding entry in the entries array, and then there was the password already cracked. So we didn't actually have to do any kind of brute force computations. We just simply do a search through the array. So the first thing the program does is grab the size of the file that we're loading in. and then allocate space for that entire file. Opens the file for reading and then pulls in the entire contents of the file all in one read statement, and then closes the file. So once we've got the entire file into memory, we now need to go through and replace all the new lines with nulls, essentially breaking up the file into individual strings. So this loop here goes from 0 up to the size of the file, and when it finds a new line character, it replaces it with a null, and then keeps track of how many times it did that so that we know how many strings are in this array. So now that we got the giant file broken up into individual strings, we now need another array. If I can look at this picture over here, we need another array that has pointers to each one of those entries. So there's a pointer here, and one here, and one here, and one here. So this statement here allocates space for that new array. We know how many entries there are, and we know that each one is going to be a pointer to a character. Each one's going to be a pointer to a string. And then we just go through the entries array, or the contents array here. And everywhere where we find a null character, we set the pointer of the next entry to the next character. And so that builds, up to this point, that builds this data structure over here. And then to do the hashes, because the hashes are all exactly the same length, we selected this time to build a two-dimensional array of strings, a two-dimensional array of characters. So each string is one dimension, and then you've got the second dimension, which is the number of hashes. So we allocated space for that entire array. And then we went through the entries array, hashed each one of the entries, copied it into our two-dimensional array, and then freed up that hash because we no longer needed it. And the last part of the program just simply prompts the user for a target string, a target hash to look for, and then it loops through the hashes array. And when it finds one, so it uses string compare, and then it just prints out what it found, and then we're done. So let's just see that program in, let's see it run. Let's do the rocku file. Where is that? Is that sitting in here? No, that's sitting up in crack 2. Okay, so it has loaded in this file. It has hashed each one of the entries. And now we can search for one of them. Let's just find, let's say, maybe this one here. And then it searches through the hashes array, and then it finds it. So that all works. But let's try a larger file. Let's do the 1 million file. Let's load that whole thing in. Oh, I'm going to load in the 1 million file, and so I probably don't want it to print out the entire array when it's done. So I'm going to comment out that section. Otherwise, it's just going to take too long to print everything out. Let me save that. We'll recompile the program, and then we'll try this again. So you can see it took a moment there to run through all million entries. But now we can search for something in there. And well, let's see. How can we search for something? What we need to do in order to search for a hash out of here is like maybe pick a random entry out of that file and hash it. How about that? Let's do that. So let's go, let's see, how do we pick a random entry of that file? So we could just look at the file. All right, and just scroll until we find one. But how about this? What you can do is you can, there's a command called shuff, which stands for shuffle. We're going to take that file, we're going to shuffle it. And then just peel off like the first entry. So we're going to jumble up the order and just look at the first entry. So there it is. But then let's run that through MD5 sum. And now here's a hash, and we actually don't know which one it is, because it shuffled up the RockU file, peeled off the first one, and then ran it through MD5, and I have no idea which one that is. So let's search for that one. Didn't find it. That's interesting. I'm a little confused why, because we should be... let's see. That's because, you know, what's happening here is when I peel off the first one there, it includes a new line character. And I don't want it to include the new line character. So let's see, how can I then get rid of that new line character? This could be a job for sed to do this. Let's see, substitute. Actually, how about this? Head-C32. There we go. So what I did here is, after pulling off one of the lines, then I said, out of that line, just pull off the first 32 characters and forget about the new line. So this should work. I hope. Let's try it. So let's run this again. Search for this. Didn't find it. Well, this is not working as well as I had hoped. Oh, I see. No, I can't pull off the first 32 characters. I have to pull off all but the last character. Let's see. Bash, remove, new line from string. I could use TR to do this. Okay. Oh, TR-D. There we go. That's what I want. Okay. And then send that through MD5. There we go. There. That's what I wanted. Okay, so if I run this command here, it'll randomly pick one of the entries out of the RockU file. It'll hash it. And then if I run this program and search for that hash, it then finds it. Now, that search didn't take very long because it's got only 1 million entries in it. And only 1 million entries, which is still quite a bit. But if we were to expand this out to the entire RockU file, which contains 14 million entries, this could take a moment. And also, if we had a whole bunch of hashes to crack, this would take even longer because we would have to be scanning through that array over and over and over again to find that hash that we're looking for. So we want to speed this up even more. And we can speed it up by organizing the arrays so that we can search it more efficiently. Let me try this. So here I've got an array of 7 numbers, and behind one of those blue rectangles is the number 89. Now, how would you go and find that number? Well, you might guess, like maybe it's somewhere in the middle. So you might pick that one there, and you realize, okay, that's 77. So where would the 89 be if that one's 77?
If it's sorted, you'd expect it to be to the right.
But this is not sorted.
Then you have no idea.
You have no idea. So maybe it's over here, right? No, maybe it's there. Oh, it happens to be there. Let's try it again. Here's 86. There it is. So if the array is not sorted, you kind of just have to guess. There, happened to be on the last one in that case. Or you could do something more systematic, like you could just start from the beginning and keep going until you find it. Okay, but if the array was sorted, then you can be more intelligent about finding the entry you're looking for. So here we want to find the number 80. Let's start in the middle. So if we find the number 53, then we know that the number we're looking for must be to the right of that 53. We could ignore everything to the left. We uncovered 79, so we know the number must be to the right of that one. And there it is. Let's try to find 72. So we'll start in the middle, then go to the middle of what remains, and then the middle of what remains. And then we're guaranteed, well, in the case of 7 numbers, how many cards do we have to flip over before we're guaranteed to find it?
3. Sorry,
3.
3.
3. We have to be able to do it in a most 3. We could get lucky on the first one, but it'll take at most 3. So in the case of a linear search, it would take at most 7, but on average about 3.5, about halfway through. But with a what's called a binary search, we can do it in at most 3. It could be as few as 1, but at most 3. So that requires that the array be sorted, and currently we have an unsorted array. So the job we have to do is sort that array into an order so that we can find things. So I think what I want to do is start talking more generally about sorting algorithms. How would you take an array and sort it? Have you heard of any sorting algorithms? Have you ever programmed one?
Yeah. Oh no, I'm thinking of search. trying to think. It's been a while. Bubble.
All right, bubble sort. Mm-hmm. So the way bubble sort works is if you have an array of numbers, let's say 9, 2, 3, 7, 12, 10, 4, the way bubble sort works is you look at consecutive numbers, a pair of consecutive numbers, and if those numbers are out of order, you swap them. So in this case, the 2 and the 9 should be sorted because the 2 should come first. So we'll take the 9 out of the way, we'll move the 2 where the 9 was, and then we'll put the 9 in place of the 2. And then we look at the next pair of numbers, and if those are out of order, you swap them. So this one goes over here, this goes here, and this goes here. Then you look at the next pair of numbers. And if those are out of order, you swap them. The next pair of numbers, now in this case, the 9 and the 12, relative to each other, are in the correct positions, so we'll leave them. Then we move to the next pair, the 10 and the 12. Those are out of order, so we'll swap those. And then finally we look at the 12 and the 4, and those are out of order, so we'll swap those as well. And now we've made one pass through the array, and the highest number has been put into the correct position. And that's why it's called bubble sort, because if you kind of imagine bubbles floating up through an aquarium, the highest number floats up to the top of the array. And then now it's in the correct position, we can make another pass through the array, which will cause the next highest number to go into the correct position. So we look at the pairs of numbers. If they're in the correct order, we leave them. If they're not, we swap them. So these look good, this looks good, this looks good, this looks good, this needs to be swapped. And now the next highest number is in position, and we keep doing this over and over again until the array is sorted. So this is good, this is good, this is out of order. So let's swap that. And now the 9 is in the right spot. And then that's good, that's good, that's out of order. Now the 7's in the right spot, and then this, and then this, and then at this point the array is sorted and we can stop. So there are here 7 numbers. Every time we make a pass through the array, one of the numbers goes into the correct position. So it would take at most 7 passes through the array. Actually only 6 passes, because once the second highest number is in position, so is the lowest number. Now, once the second lowest number is in position, so is the lowest number. So it takes 6 passes to go through the array. And each pass needs to look at 6 pairs of numbers. So we have 6 passes, 6 pairs on each pass. So it's 6 times 6 equals 36 comparisons, 36 potential swaps that we have to do in order to sort the array. If we had an array of 10 elements, there would be 9 passes and 9 pairs on each pass. So we got 9 times 9 equals 81 potential, certainly 81 comparisons and potentially 81 swaps that we have to do. If we have 100 elements, then it's 99 times 99, or 9,801 comparisons to do. And if we have 1,000 elements, it's 999 times 999, which is, well, you know what? Once we get into numbers that big, it doesn't really matter that we're subtracting 1, right? The difference is really kind of minor. So in general, if we have n elements, we have something on the order of n squared pairs, or n squared comparisons. to look at. So if we have 1,000,000 entries, then we're talking about, what, 1,000,000,000,000 comparisons to do. And that could take a very, very long time. Even on the fastest computers, it could take a very long time. And so bubble sort happens to be a sorting algorithm that's easy to implement. Beginning programmers can implement this with just 2 loops. But it's slow. So there are faster algorithms out there. They're more complex to implement, but they're much faster. Do you know the names of any of those? So while I'm asking, I'll point out that the computer science way of representing this is capital letter O and then n squared. I like to think of that capital letter O as meaning like on the order of. It takes on the order of n squared comparisons to sort the array. It's actually n squared over 2 because as you make passes through the array, each pass gets shorter and shorter. So the first time you have to look at n minus 1 pairs, then you have to look at n minus 2, then n minus 3, n minus 4. So the passes are getting shorter, and you can really cut the number of comparisons in half. But we're talking about the difference between 1,000,000,000,000 comparisons and 500 billion. You know, what's a few billion? So there's sorts like merge sort, selection sort, insertion sort, quicksort, heap sort, BOGO sort. There's a whole bunch of sorting algorithms out there, and they all have their pluses and minuses. Like some sorting algorithms are faster. Some of them are faster because they use more space, so they may make temporary copies of the array in order to sort it. Kind of like if you had a deck of cards, you might make some temporary piles of cards in order to assist you in sorting out the cards. So let's take a look at a visualization of bubble sort versus quicksort.
Our task is to sort these balls by brightness. This robot, however, is short-sighted and can only compare balls when they are placed directly in front of its eyes. Bubble sort compares every adjacent pair of balls, moving the brighter ball forward. This brings the brightest ball to the end of the row, where it should be. Another pass is performed on the remaining unsorted balls. And so on. Quicksort starts by randomly picking one ball, called a pivot. It then rearranges the other balls by comparing them with a pivot. Balls brighter than the pivot are moved to the right, and darker ones to the left. The pivot can now be placed where it should be. Our row of balls is now split into 2 smaller, unsorted rows. Each is sorted in turn using quicksort. Pick a pivot. Rearrange the other balls. Put back the pivot. And so on.
That poor little guy keeps he's still going at it. Oh, it's finally done. So as you saw there, bubble sort is slower on average than quicksort is. Now, quicksort is an algorithm where its worst case complexity is actually the same as bubble sort. But that doesn't happen on average. The worst case is like every single element is exactly out of order and it has to swap everything every single time. But usually an array is randomized, and then quicksort performs better than bubble sort on average. And it works using a divide and conquer approach. It takes the array, it cuts the array, and it finds like the middle element of the array, and then it moves all of the elements that are larger than that, what's called the pivot point, to the right of it, and it moves all the elements that are smaller to the left of it. And then it cuts each one of those arrays in half, and then performs quicksort on each half. So then it finds the middle element, it moves the elements back and forth, and then cuts it in half again. And it keeps doing that until you got an array of size 1 or 2, and then from that point forward, everything is sorted, and then it kind of merges things back together. Not really merges things back together. Once it does that and cuts them all in half, then the array is sorted. And so quicksort can work very, very quickly. In fact, I saw some discussions here on the YouTube chat about which one is faster. Is bubble sort or selection sort faster or slower? And I happen to have a video for that one as well. So let's take a look at that.
This short-sighted robot will now demonstrate insertion sort. First, let's assume the left half of our input is already sorted. We'll now add the next element to the sorted part by moving it left until we find where it belongs. We'll compare it with its left neighbor. Since the neighbor is brighter, we'll swap. We'll continue until we find an element darker than the one we're adding. This is the right spot for it. We'll now repeat the same steps with the next unsorted element. And so on. Now let's start from the beginning. The first element by itself is already a sorted sublist. We'll extend it by adding new elements, same as we saw before. The two algorithms share some similarities. Both work in iterations, extending the sorted part one element at a time. So why did insertion sort win so decisively? Let's replay the entire match. We'll focus first on bubble sort and draw a mark on this chart for each comparison it makes. In this variant of bubble sort, the iterations gradually get shorter. It skipped the last two iterations thanks to its ability to detect when the list is already sorted and stop. But starting from a random permutation, this optimization is only likely to occur near the end anyway, so the number of comparisons is roughly n squared divided by 2. Now we'll draw the same chart for insertion sort. Insertion sort starts with the shortest iteration, and they gradually get longer. But it doesn't bother running each iteration all the way. It stops when it finds the correct spot for the newly added element, which on average happens in the middle. Therefore, the number of comparisons here is approximately n squared divided by 4. So no wonder insertion sort won. Now let's draw a similar chart for an algorithm we've shown in previous videos, quicksort. Thanks to its divide and conquer strategy, the height of this chart is proportional to log n on average. So the total number of comparisons is proportional to n log n on average. The difference between n log n and n squared gets more pronounced as n grows.
So, those of you who are discussing the difference between bubble sort and insertion sort, you're correct. Insertion sort does operate more quickly on average than bubble sort, but it's almost what am I going to say? It's the difference between n squared over 2 versus n squared over 4. If you were to plot the number of elements versus the time it takes. Here's, let's say, n squared. N squared over 2 might look like this. And n squared over 4 might look like this. You can see they all have the same, like, bowl shape to it. And that's what we're mostly concerned about, is what's the shape of that graph, not how steep or shallow it is. So all of those algorithms, bubble sort, insertion sort, selection sort, take on the order of n squared. If it's n squared over 2 or n squared over 4, that doesn't matter so much. What matters is the shape of that curve. Now, what about n times the log of n? Well, that still has a bowl shape, but it's actually way less shallow, way more shallow. It never approaches anything like n squared divided by some constant because it stays much shallower. And so an algorithm like quicksort operates much faster than any of the n squared algorithms does by a huge factor. And so although algorithms like bubble sort and insertion sort are easy to program, they operate pretty slowly. Quicksort is more complex to program, but it's one of the fastest sorting algorithms. And there's a whole class of them like merge sort and heap sort. I think heap sort that falls into the same, anyone that uses a divide and conquer strategy is going to have a time complexity of about n times log of n. So let's take a look at how to do sorting in C. We can implement something like bubble sort, and then we can take a look at quicksort. So what I'm going to do is I'm going to start out by just defining an array of numbers, so I don't have to type in numbers every single time. And I'm going to start with just with numbers because numbers are fairly straightforward to do. And then we're going to sort it using bubble sort, and then print out the array and just show that it's all been sorted. So let's define the size of the array to be, let's do 10 elements. And then we'll go, let's see, integer array of size equals, and let's just put in some numbers. 9, 4, 2, negative 5, 0, 1, 10, 12. How many is that? 1, 2, 3, 4, 5, 6, 7, 8. I got 2 more to do. Let's do 7. And then let's put in another negative number. Let's put in negative 8. So now we're going to do a bubble sort on this. So the algorithm for bubble sort is to make n minus 1 passes through the array. And then on each pass, look at n minus 1 pairs of numbers and swap them if necessary. So this outer loop here is going to control the number of passes. And then we'll have another loop inside. That's going to look at size minus 1. Oh, this is going to be, I'm going to change the variable here. This is going to be j. And then we're going to look at the jth element of the array and the j plus 1th element of the array. And see if they're out of order. So if the jth element of the array is greater than the j plus 1th element of the array, then we're going to swap them. And this is our standard swap algorithm. You create a temporary variable, you move one of the elements into that temporary variable, then you move the second element into the first spot, and then move the temporary back into the second spot. So that's bubble sort. Very easy to program. 2 loops. And then we'll print out the array. I was going to print it out vertically, but I think actually I'll print it out horizontally, just so it's easier to see. Now, these are the kinds of decisions that really vex me. It's like, should I print it out horizontally or vertically? Nah, I'm going to go with vertically. Okay, so let's go for it. So when we print it out, they should be arranged in numeric order, starting with negative 8, then negative 5, then 0, 1, 2, and so forth. And there it is, negative 8, 5, 0, 1, 2, 4, 9, and up and up. Okay, so now I kind of want to make things really interesting. And that is to create an array and then just fill it with random numbers and then sort it. So if I want to be able to create an array with, say, 10,000 elements, I actually can't allocate it on the stack like this because there's a limit to how big the array can be on the stack. Maybe 10,000 is still not big enough. Maybe if I go up to 1,000,000, that might start exceeding that size. So I can't allocate on the stack. I'm going to have to allocate it on the heap. So let's change this and let's make it int pointer array equals malloc size times the size of an integer. And now we're going to fill it with random numbers. So to fill it with random numbers, we're going to need standard library and time.h. If you remember how to do random numbers, we have to seed the random number generator. And then we will generate a random number every single time we access the element of the array and fill it with that number. And so we're going to go array sub I is equal to random. And then why don't I do a mod, let's say the size of the array, so the numbers don't get too excessively big. Otherwise, what will happen is you generate a random number, they're like all going to be in the range of like 1 to 4 billion because that's where the majority of the numbers lie, and it's just not that interesting. So I'm just going to go with a mod on the size. Okay, so let's compile this and run it. And did you see that brief, very brief pause there while it did the sort? Let's increase the size of the array. Let's go up to 100,000. So is this going to take 10 times longer or more than that? So I increased the size of the array by 10. I went up by a factor of 10. How much longer is this going to take? What do you think? I see people on YouTube have been arguing over the math here. So here's a question for you. How much longer is this going to take? I increased the size of the array by a factor of 10. It took about a second for it to run before. It's clearly taken more than 10 seconds more. It's actually going to be 100 times longer. Remember, bubble sort is an n squared algorithm. So if I make n 10 times bigger, n squared is going to be 100 times. So this is going to take on the order of about a minute or more to run. And I think it did. In fact, we can put the word time in front and then run this again, and it will tell us how long it took. So now, essentially, the computer is running a stopwatch on this. It gets the time when the program starts, gets the time when it ends, subtracts the two, and then it gives us the duration. Now this may take slightly more time. It may take slightly less time because we've got a new random array here. So we never know how it's going to come out. But it should finish up in just a second. There. So it took almost a minute, 56 seconds to run. And if I was to increase the size to 1,000,000, we would now expect this to take, well, 100 times longer. So maybe close to, what would that be? Over an hour. So you can see bubble sort, even on a fast computer, is pretty slow. So what about quicksort? Well, as I said, quicksort is more complex to program, and you can find algorithms out there on the internet, and you can plug them into your program. But quicksort is already part of the C standard library. There's already a quicksort function built in, so we're going to make use of that. Before I show you how to use the function, let me bring forward one thing in particular. You notice that central to the bubble sort algorithm is this comparison and swap. And if you remember those animations of the sorting algorithms, you remember the robot holding up the balls to its eyes, that every time it held up a pair of balls, that was that comparison. So no matter whether it was quicksort or bubble sort or insertion sort, all of them did this comparison. Take two elements and compare them and decide whether they need to be swapped or left alone. Every single sorting algorithm out there is going to have some kind of comparison in it. Now, this is an array of integers. What if we wanted to do an array of floats? What would we have to change? Well, it would be not an integer array, it would be a float array. We'd have to use size of float here. But pretty much everything else would be the same. You compare floats just like you compare integers. You still use less than or greater than or equal to. This would have to be float here. And then when we print it out, of course, we'd have to use %f instead of %d. But more or less, the sorting algorithm itself doesn't change a whole lot. Now, what if we were sorting strings instead? If we were sorting strings, of course, our malloc would be different. It would be like size of character pointers, and our array would be different here. We'd have character pointers instead of integer pointers. But what about the sorting algorithm itself? What would have to change in there? Right, we would have to use string compare instead of greater than or less than. So the comparison function would be a lot different. We can't compare strings like we compare numbers. We have to use a function for doing that. And of course, the swap would be a little bit different. It would use string copy instead of just using the equal sign, because the equal sign is just going to transfer addresses around. But we don't want to do that. We actually want to copy strings around. So we'd have to use string compare here, and we'd have to use string copies here. So what this means is that if you're going to write a general purpose sorting function and provide it in a standard library, you don't know ahead of time what kinds of things are going to be sorted. It could be numbers, it could be strings, it could be things that are more complicated than that. But nevertheless, there is going to be some kind of comparison between two elements. So with the built-in quicksort function, there are 4 parameters you have to pass in. The first parameter is a pointer to the array that you're sorting. Well, that makes sense, right? And you also have to tell it how long the array is. So you also have to pass in the number of items. And you have to tell it how big each item is, because this is a general purpose sorting function. It doesn't know what you're going to be sorting. You could be sorting integers, which are 32 bits. You could be sorting floats, which are also 32 bits. You could be sorting doubles, which are 64 bits. could be sorting strings, which have a different size. So you have to pass in the array that's being sorted, the number of elements in the array, how big each element is, and then the fourth parameter is a function that compares two elements. Okay? So 4 parameters. The array you're sorting, how long the array is, how big each element of the array is, and a function that compares two elements. So every time the sorting function, the sorting algorithm, needs to compare two elements, it's going to call your function, pass it two elements, and then your function compares those two things and then tells it, are they in the correct order or do they need to be switched? In some programming languages, this is called a callback function. You call a function, and then it calls your function periodically in order to do some work. Okay, well, actually, let's switch over here. Let's go ahead and try to do this here. So we're going to call quicksort. I'm going to comment out the bubble sort. And we'll do quicksort. So we'll call quicksort. We pass in the array to be sorted, which is ARR. We pass in the length of the array, which is size. We pass in the size of each element, which is, it's an array of integers. So we're going to pass in size of int. And then finally, the name of a function that's going to compare two elements of the array and indicate whether they are in the correct order or not. Let's call it, and it's going to be one of our functions, right? So we can call it whatever we want. Let's call it, I don't know what to call this thing. Let's call it, I don't know, int compare, okay? Compares two integers. And so by passing in the name of a function, you're essentially passing in the address of where that function lives in memory. It's a function pointer. It's a pointer to a function. Okay, so what does this comparison function look like? Let's go ahead and look at this again here. So this right here is essentially the function prototype for this function. It is, let's see, how do we read this here? It takes in two parameters. Each one of them is a void pointer, and it's declared to be constant so that we don't change the values themselves. So you're passing in two void pointers, and you're returning an integer. Okay, so let's break this down. What's a void pointer? A void pointer is C's way of saying it's just a pointer to something. It doesn't matter what it is. It's just an address. It's kind of similar in Java to the concept of object. There's a class in Java called object, which just is an umbrella class for everything else in the language. So you can think of void pointer as being kind of like object. It's just a pointer to something. We know it's an address, but we don't know what it is. And this is how you handle things like generics in C. You pass in void pointers. So we have to declare our integer comparison function this way. So let's do that up above. Let's do it up here. Int. I'll call it int compare. Remember, that was the name of the function. Const void pointer, and I'll call this A, and const void pointer B. So let's take a look at what that is. 9, 3, 7, 2, -8, 4, 6. So as we're doing this sort on this array, it's going to look at two elements, a pair of elements, and then ask your function, are these in the correct order or not? So it's going to pass these two elements to you as A and B, but A and B are not the values 9 and 2. They're pointers to the values 9 and 2, okay? So what it passes to you is not the elements themselves, but pointers to the elements. And the reason for that is the elements could be much larger than just a number. They could be like a structure, or they could be an array, right? So it's going to just pass you an address. So A is a pointer to an element, and B is a pointer to an element. Okay, so they come into your function as A and B, but they come in as void pointers. What are they actually? They come in as void pointers, but what are they actually pointing to?
Integers.
They're actually pointers to integers. So the first thing we have to do is cast A and B to be what they actually are. So A and B are void pointers. Let's go integer pointer, let's call it AA. Let's cast it to be an integer pointer because that's what it actually is. So these are my typecasts right here. You just put parentheses out in front of a variable name and then put the type inside of there, and then it changes the type. So the question is this how you do generic programming in C, doing void pointers? And this is as close as C gets to doing generic. What C doesn't have that other languages do have is things like function overloading. I can't make two functions with the same name that have different parameters in C. That's been a proposal for a couple of years, not more than a couple of years, for maybe a decade or so, to add that to C, but so far it hasn't made it into the language. There's been a decision by the C committees not to do function overloading. In fact, I just looked at the latest, I think it's called C23, which will be the version of C that comes out next year. And it still doesn't include function overloading, even though I was really hoping that it would. But it doesn't. So that means when you have functions that want to have the same name but operate on different parameters, you actually have to give them different names. Okay, so the comparison function, it doesn't say here. The comparison function returns 0 if A is equal to B, a negative number if A is less than B, and a positive number if A is greater than B. And when I say equal, less than, or greater than, I mean like in the sense of whatever the type is, right? So if it's strings, you're going to do string comparisons. If it's numbers, you're going to use less than or equal to. You just need to return 0 if the numbers are equal, or if the values are equal. A negative number if the first one comes before the second one, and a positive number if the first one comes after the second one. So let's do that. Let's go if AA is equal to BB, we'll return 0. Else, if AA is less than BB, return a negative number. It doesn't matter what the number is as long as it's negative.
Can't see your screen.
Oh, sorry about that.
Thanks.
Okay, So if the two numbers are equal, return 0. If AA is less than BB, return a negative number. Otherwise, return a positive number. And as I said, it doesn't matter what the number is, as long as it's positive or negative. Okay, let's give this a shot here. Oops, not that. Compile again. And let's run it. So remember, we've got an array with oh, I added a 0. So this is going to be 100,000. And if you remember, oops, here we go. If you remember, before it took about a minute to sort the array with 100,000 elements in it. And let's try it now with quicksort instead of bubble sort. And you can see it's almost instantaneous. So let's try it with 1,000,000 entries in there. And in this case, since there's so many entries, I'm not going to have it print out the array. I'm just going to have it print out the word done. Oh, wait a second. It's not, doesn't appear to be sorted. So what happened there? Let's let's just double check this is all working correctly. What do we got to do here? Let's put this back to 100,000. Let me make sure we compiled it correctly. And are we in fact calling quicksort? We are. Passing the array, the size of the array, size of integer, and then int compare. And let's make sure our int compare is working correctly. If AA is equal to, oh, I see the problem here. Do you see it? Actually, people on YouTube are already saying like, hey, I see what the problem is. Remember, AA and BB are not integers. They are pointers to integers. So I need to dereference each one of these. Otherwise, I'm just comparing their addresses. Okay, now let's do this. Do this for real. There we go. That's what I'm looking for. Now the numbers are sorted. Okay, so let's get rid of this printing here. And let's just print out the word done. So the vast majority of the time spent running the program was just printing things out. Notice the actual time to sort this array is about 0.02 seconds. Remember before it took a minute to sort the array. Now it's less than 1/10 of a second. So let's bump up the size of the array to 1,000,000. So I increased the size of the array by a factor of 10, and the time went up to 0.2 seconds. Let's go up to 10,000,000 entries in the array. Two and a half seconds. You can see how much faster quicksort is than bubble sort. I mean, it's not just like it's a little bit faster. It is incredibly faster. When the size of the array gets much larger, quicksort is hugely faster than bubble sort. Remember that graph over here, right? As the size of n gets bigger, this graph goes up and up and up. It gets steeper and steeper and steeper, whereas the n log n one continues to just kind of like go up gradually. Okay, so that's quicksort on a bunch of integers. What about quicksort on a bunch of strings? Does C have other sorting functions or just quicksort? I think the standard library just has quicksort. I haven't dug too much into it, but quicksort is good enough for most purposes. Oh, by the way, in your integer comparison function here, we did if the thing that A is pointing to is equal to the thing that B is pointing to, return 0. If the thing that A is pointing to is less than the thing that B is pointing to, return -1, otherwise return 1. There is a shorter way to do this, a quicker way to do this. How about this? Return the thing that A is pointing to minus the thing that B is pointing to. So let's say A and B are both pointing to the number 3. If you subtract them, you'll get 0. That's what we wanted, right? And if A was 1 and B was 4, so A comes before B, if we subtract them, we'll get a negative number. And if B was the bigger number, if B was the smaller number and we subtract them, then we get a positive number. So subtracting the two values is a quicker way to return exactly the values that we're looking for. Let's go ahead and compile it and run it. And it takes about the same amount of time. So if you're comparing strings instead of numbers, what would the inside of this function look like? Well, first we need to cast A and B to be the correct things. So in this case, A would be pointing to a string, and B would be pointing to a string. And then we can just return what string compare returns. Because string compare already returns 0 if A and B are equal, and it returns a negative number if A comes before B, and a positive number if B comes before A. So this is how you would sort strings. You'd still call quicksort. You still pass in the array, the size. This would be the size of character pointer, because each one of them is a string. And then you just pass in your string compare function here. Now the question might be, why can't we just pass in string compare itself? Why can't we just put strcmp here? And the answer is, well, you can't, because of the fact that string compare takes in 2 character pointers, but our string comparison function that's used by quicksort takes in 2 void pointers. And so you're going to get a type conflict. So you have to wrap up string compare inside of your own function that just does the cast correctly for you. Won't string compare automatically do the casting? I don't think so. You know what we can do is we can just go string compare right here and then see if it compiles. It doesn't. Oh, let's go ahead and include string.h. So it doesn't. Incompatible types. It says string compare is expecting void pointers, and string compare is expecting character pointers, and we're passing in void pointers. So we get a type conflict. But if we change this to string compare, our version, it compiles fine. So the upshot there is you cannot just pass in string compare and have it work. Okay, well, we have about 3 or 4 minutes left. We didn't quite get to what I wanted to get to, which was how can we essentially sort this. You remember this was the original program we wrote. We have 2 parallel arrays. And I want to be able to sort the hashes array so that I can do a search on them quicker. But the problem is that if I just sort this array, then it leaves this one unsorted. And the entries don't match up to each other. So I would have to sort this array, and anything that I did to the hashes array, I should also do to this array so that they line up. The problem is the built-in quicksort function doesn't know how to operate on 2 arrays. It only knows how to operate on 1 array. So the solution there is to combine these 2 arrays together and make them into 1 array. Can you guess how to do that?
Yeah, use the structure.
Exactly. So we could combine those 2 arrays into 1 by putting each element of the array into a structure and then building an array of structures. So we could have like a character password, let's say up to 20 characters, and then character hash, and we know that's going to be 33. And then all we have to do is just sort the array of structures, but by hash value, and then we can search it pretty efficiently. Question was, can I check whether the sorting happens correctly with this string compare? It's not going to, because now it's going to treat each integer as though it was a string, but it's not going to look at like the digits. It's going to look at the binary values of them, and that's just going to be like terrible. So I'm guessing it's probably, well, now I'm curious, right? Is it going to work? Well, it just said done, right? Because I didn't print anything out. Let's make this smaller. Yeah, it's all just jumbled up. And part of that is because you can't sort numbers in the same way you sort strings. When you sort numbers, you have to look at the whole number. Or essentially, when you sort numbers, well, when you sort strings, like you look at the first character, and then if that disambiguates them, then you can sort those correctly. But if the first character is the same, then you look at the second character. And if those characters are the same, then you look at the third character. And it doesn't work like that. It doesn't work that way with numbers at all. So I think what I want to do next time, when we come back on Thursday, is we'll take a look at sorting an array of strings. And some people in the chat are already trying to figure out how that would be done. And we do have a program that loads in an array of, actually, if you don't mind, we've got a few minutes. Why don't we just try to get this program to kind of do exactly that, to sort these strings. Want to do that? So I'm going to make a copy of this. Copy load file.c. Let's call it load file2.c. And then this is what I'm going to modify. So this program already loads in a file that contains a bunch of strings. I'm going to strip out the stuff that hashes them. And we're also going to strip out the stuff that searches. We'll get to that later.
We can't see your screen.
Oh, goodness. Okay, so what it is, I pulled out the stuff that builds that second array of hashes, and I also pulled out the lines of code that does the searching. All I want to do is read in this file of passwords and then just sort it. And then we'll get next time to sorting the hashes. But this time I just want to sort a bunch of strings. So if you remember, we had a picture that looked like this. We had all of those strings are contained in one array called contents. And then we had another array called entries. And each element of entries pointed to one of these elements of contents. And the reason for that was, one, it allowed us to read in the whole file all in one fell swoop and then make pointers to each one of those strings. But also, because each one of these is like of a different length, it doesn't lend itself very well to doing a two-dimensional array. So this second array that points to each one of those strings is probably an easier way to handle this. And for sorting purposes, this is really nice, because now we don't actually have to move these strings around. We can leave them where they are. We just move the pointers around. Right? And the pointers are all just 32-bit or 64-bit values. So we don't have to copy strings. We just have to move addresses. And that's going to be a lot faster. So what we're essentially doing is we're going to be sorting this array. We're going to be sorting this array of addresses. Does that make sense? So let's call quicksort. We're going to do it on entries. We know how big it is. It's stored in a variable called num entries. And then how big is each one of these? How big is each one of these things? Or what type is it? Well, each one of those points to a character. I mean, they actually point to strings, right? But each one of those addresses is the address of a single character. So that means each one of these is a character pointer. And then our string comparison function. Okay, so let's take a look at, first of all, the cast, and then the comparison we have to do. So as the sorting function goes, we've got A and B, A points to one of these things and B points to another one of these things. So they're passed into our string comparison function as void pointers, but what are they actually?
They're character pointers.
No. Remember, each one of these is a character pointer. And A points to one of those things.
So a pointer to a character pointer.
Yeah. So this is a character pointer. And this is a character pointer. Okay? So each one of these array elements is a pointer to a character. So if A points to that, those must be pointers to character pointers. So here's the cast we have to do. Take A, cast it as a character pointer, and then assign that to a variable. Do the same thing for B. And now we can just return string compare. We're going to pass in AA and BB, but what string compare expects a character pointer, and AA is a character pointer. So how do we get AA to be the correct thing?
So we have to dereference it.
Yep. And that's what our string comparison function looks like. Now, let's return to the bottom of this and print them out. Okay, and let me just do one last check here. I have string.h. I don't need MD5 because we're not using that anymore. And everything else looks okay. So let's compile that. And we'll run it, and we'll pass in, we'll do the Rocky 100 file, which contains just 100 entries, and see if it works. So it should load the file in, construct that second array, sort that second array without moving the strings themselves, and then print the whole thing out. And there it is. It's nicely in alphabetic order. So if we do it for the Rocky 1000 file, that works fine. If we do it for the 2000 file, that works fine. If we do it for the 1 million file, of course, we'll spend all of our time printing it out. So let's remove that bit of code. And let's just print out done. Pretty nice. It sorted 1 million strings in probably less than a second. Yep, about a quarter of a second. So that's pretty darn quick. And if we did bubble sort on this, we can imagine it would take a fairly long time to do. I know, isn't that amazing? Like the speed up is just incredible. And I'll have to tell you a little story. And I may actually do a separate like live stream on this. Like you can barely see it, but I have these old computers back here. So, and there's one in my closet there. That's an Apple II computer from the early 1980s. It runs at a blistering 1 megahertz. Not 1 gigahertz, 1 megahertz. So it's, on the order of 3,000 to 4,000 times slower than our current computers. And it has only 64 kilobytes of memory. 64 kilobytes. And so I had this idea. This game that's like all the craze right now called Wordle, where you have to guess the 5-letter word, and you have 6 tries to do it, and it tells you whether you have a letter in the correct position, or you have a letter that's in the wrong position, or you just have the wrong letter. You know about this game I'm talking about? And so I thought about, well, how could I implement Wordle on one of these old computers? And if you've dug into the Wordle source code at all, you realize that the word list is actually just built into the game. So if you want to cheat, all you have to do is look at the JavaScript code, and there's all the words. But anyway, so I obtained that word list, and then I wrote a basic program, an Apple basic program, to load that file into memory. Now, there's about 2,000 words in that list, and each one is 5 characters long. So each string in the Apple computer takes up about 6 to 7 bytes. There's the 5 bytes for the string itself, plus you have to have 1 byte for the length of the string, and then I think there's a little more overhead. So loading that entire word list into memory not only takes about 10 or 15 seconds to do, but it uses up 17 kilobytes of the available 35 kilobytes for my program. So about half the computer's memory is spent just holding all of those strings. And then if you were to implement the game itself, you would prompt the user to type in a word. And the first thing you have to do is check to make sure that the user actually typed in a valid word. So you have to search that list for the word they just typed in. So I wrote a program to do that. It loads the word list into memory. It prompts the user to type in a word, and then it searches that list for that word. Well, guess how long searching that list takes in BASIC? It took about 10 seconds. Now, to me, that doesn't make a very interactive game. You type in a word, and you have to wait 10 seconds for it to tell you whether or not that was a valid word or not. And then it hasn't even gone to the point of like highlighting the letters in yellow or green. Right? Just searching that list takes about 10 seconds. Because that list is an unsorted list. We have to do a linear search from beginning to end. So I had this idea. Why not sort the list? If we could sort the list in memory, then we could do binary search on it, and it would go much faster. So I set about to do that. So I wrote a program that would load the word list into memory and then do bubble sort on it, because bubble sort's easy to program. Very easy to do in BASIC. 2 loops, just like I did here in C, 2 loops, do some string comparisons, and then swap them if necessary. Guess how long that took? Remember, it has to make roughly 2,000 passes through the array. And each pass has to compare about 2,000 pairs of words, and then swap them if necessary. So we're looking at a total of 4 million comparisons. So I had the sorting routine print out the pass number every time it made a pass through the array. And it would say pass 0, pass 1, pass 2, pass 3, pass 4, showing me which pass number it is. Every single pass took about a minute, maybe a little bit more. So we're looking at roughly 2,000 minutes to sort this array of 2,000 words. How long is 2,000 minutes? It's about 33 hours. So we're looking at about a day and a half. to sort 2,000 words. I could probably all do it by hand faster than that. So then I thought, well, why don't I do this with quicksort? Well, I'd never implemented quicksort in BASIC before, and here's some limitations of BASIC on 8-bit computers. You don't have any local variables. You only have global variables. And you can call subroutines, but your stack depth is really shallow. You can only call to a depth of about 8 to 10 subroutine calls. And if you're sorting a list of 2,000 words, you remember that diagram of how deep that stack depth is? If you're doing 2,000 words, well, the log of 2,000 is like about, what are we looking at, 10? About 12. And already that's deeper than the stack depth that BASIC allows. So it took me about 5 hours to implement quicksort in BASIC with only global variables and no stack. What I had to do was I had to remove all the subroutine calls and just replace them with what are called go-tos, and I had to implement my own stack. So I basically had an array that held all the local variables that were needed to recursively call itself. So again, about 5 hours of programming, and then and debugging. Right, it didn't work correctly the first time, but when it finally worked, I was able to sort all 2,000 words in about a minute and a half. Okay, so you're probably thinking, golly, a minute and a half to sort 2,000? I mean, our computers can sort that in a fraction of a second. But remember, it was going to take 33 hours. It was going to take a day and a half. And I shortened it to a minute and a half. So quicksort is a lot faster than bubble sort. And so I thought someday I would do like a YouTube live stream and show how I coded up quicksort in BASIC using only global variables and no subroutine calls. And then once we had that, we would then be well on our way to being able to do Wordle, because now we could very quickly, I haven't implemented binary search yet, but very quickly determine if a word is in that list. And then from there, actually showing the colors is relatively easy to do. So the upshot there is quicksort is a lot faster than bubble sort. And it's made really, really obvious when the arrays are huge on a modern computer, or even if the arrays are a modest size on an old computer. Anyway, I thought that was really interesting when I did that. It was about a week ago when I've done that. And you know, when quicksort finally worked, I mean, you cannot imagine like well, you probably can imagine like the feeling of like, wow, it actually worked. You know, actually I had it printing out its progress, and I could see the numbers. I could see the stack depth growing and shrinking, and I was like, wow, it's growing and shrinking the way it's supposed to. It's not going out of control. Which is what I was worried about, that I didn't implement the recursion correctly. So when I saw the stack depth going up and down, I realized this is actually working. And then when it finally printed it out, I was like amazed. It's like, it actually worked. So I thought that was really cool. When I did basic programming back when I was a kid, I knew how to do bubble sort. I'd been taught that, but quicksort was just beyond my comprehension. I never heard of anything like that. It wasn't until I got to college when I heard about quicksort. And here was an opportunity to implement quicksort on an old 8-bit computer. Why didn't BASIC have local variables in a stack? I don't know. It was just probably, for one thing, wasn't in the use case for BASIC. And, you know, BASIC was just supposed to be a language for beginners to learn on. And probably local variables were pretty uncommon in languages back in the 60s and 70s. It wasn't until things like Pascal came along and eventually C when he had local variables. Implementing local variables means implementing a stack that can hold. So basically, if you only have a call stack that just holds return addresses, that's easy to do because every entry in the stack just contains the address of the line number you came from. So the stack is even if you have, let's say, 10 calls, each call is only 16 bits, and so you're looking at a total of 20 bytes for your stack. But if your stack also holds local variables, then the stack can get bigger and smaller, and you might not have enough memory for it. So it's easier just to do global variables for everything. Then you don't have to maintain separate symbol tables. You don't have to maintain anything other than one symbol table for your entire program. So that's maybe this summer or something. When I have more time, I might do that. Well, I think we've reached probably the end of today. So on Thursday, we'll come back and we'll learn how to load an array of structures, and then how to sort those structures based upon one of the entries in the structure. So we could have, let's say, we've seen an array of structures before. It was an array of landmarks with the name of landmark and latitude and longitude. And then we could sort those by landmark name, like we could sort them alphabetically. Or we could sort them by longitude, so we get all the landmarks from east to west, let's say, or west to east. So that'll be on Thursday. And then if you're watching my other live streams on Wednesday, we're going to start talking about finite state machines. And that'll lead into pattern matching and a discussion about how compilers and programming languages work. And someone here made the correct observation that if you're doing the stack to hold local variables, now you need to hold local variables, you need to hold parameters, and you need to hold return addresses. And computers back then just didn't have the kind of memory to do those sorts of things. When your operating system takes up 20 kilobytes of your available memory, your program code has an available 35 kilobytes, and then you've got another few bytes for the ROM, you run out of memory pretty quickly. So you need a programming language that just doesn't use a whole lot of memory.
Sorry, when was that about the finite state machines?
Oh, that's Wednesday.
Is that your discrete structures class?
Exactly, yeah.
But that's streamed on YouTube as well?
Yep. So we'll finish up this password cracking either this week, or we'll dip a little bit into next week, probably on Tuesday, just to wrap up all the concepts we need to throw together this one last program, and then we'll start getting into computer networking. Okay, well, I think that's it for today.
All right. Well, thank you.
You're welcome.
Have a good rest of your day.
You too. Take care.
All right, bye.
Bye-bye. And then the folks on YouTube, I'm sorry I didn't get a chance to see all the conversations you were having about sorting complexity and time, but it looks to me like that second video that I showed kind of covered a lot of the concepts that you were talking about, as far as is insertion sort quicker or slower than bubble sort, and by how much. And then I do see a lot of the comments here about how much faster quicksort is than bubble sort. I mean, it's just amazing how much faster that is. When the array gets really big, quicksort wins massively over bubble sort. Where can we find those sorting videos? So those particular ones were on this channel. Oh, stop. There we go. Here's the name of the channel. Whoops, right there. So in addition to some videos about sorting, there's also videos, all computer animation about quantum physics and what else here? The halting problem, synchronization problems. So not too many videos there, but all of them really pretty good explanations of the concepts they're trying to illustrate. Do I have a website? Not really. I mean, you can find me on Twitter, but I don't say a whole lot. I guess my website is YouTube. All right. Well, we'll come back on Thursday and we'll continue, like I said, our discussion about how to sort structures and how to search them. So we learned today about using quicksort, and on Thursday we'll learn how to use the binary search function that's built into the standard library. And that'll be, so once we can sort and search, we'll have pretty much all the pieces that we have that we need in order to be able to do this final password cracking program. All right. Yep, take care everyone. Enjoy the rest of your day, or get some sleep if it's nighttime for you. And I'll see you next time. Be safe, take care. Bye-bye.